Hi, welcome to another practical session in which we are learning spatial statistics and spatial econometrics with R. My name is Saif, and today we will continue our discussion of spatial regressions in R. So, we will try to develop the programming skill needed to run spatial regressions in R, but this skill can only be acquired based on a solid understanding of the theoretical principles. And what we need to understand in order to fully appreciate the programming that we will do in this session is the idea of linear regression using ordinary least squares, the assumptions that we make before we run OLS, what is spatial autocorrelation and how it violates those classical assumptions, as well as an understanding and familiarity with the basic spatial models, the SLX, SAR, and SER models. In the last session, what we did was we prepared our spatial data for regression analysis. If you recall, it was groundwater levels data, and we were trying to explain groundwater levels in space using some observations on rainfall, temperature, and cropping. So trying to combine climatic and anthropogenic factors to explain the groundwater level over a region of space in Uttar Pradesh. So we prepared this data and we built our neighborhood or weights matrix that is required to indicate the spatial relationships in our region. We need these two steps before we start running our regressions. I will briefly review these steps for those of you who might have missed the last session. If you did miss the last session, I encourage you to pause the video now, go back and watch that session, which was session 8, which was part 1 of spatial regressions, so that you have a firm and clear grasp of how to prepare the data for regression analysis and how to build your weights matrix, your neighborhood or your adjacency matrix. Once we've done that, we will today start to actually run the spatial regression models using R, and then we will look at the results and try and compare what are the differences between the results when we run different models. So quick review, this is something that we should already know, but just to refresh your memory, there are 3 simple spatial regression models. The first one is the SAR, or spatial autoregressive model, in which we include on the right hand side a spatially lagged version of the dependent variable. So this W, which is the weights matrix, indicates the neighborhood relationships, and this rho is the coefficient of this spatially lagged variable. The W times Y is the spatially lagged version of Y. So if Y is groundwater level at location I, then WY is the groundwater level in the neighborhood of I, in the neighbors of I. So if we are in a sub-district, let's say Agra sub-district, then WI will be all of the neighbors, or WY would be all of the neighbors of that sub-district. And how we would pick out the neighbors is because the weights matrix will contain 1s for all of the neighbors and 0s for everything else. So we are trying to explain groundwater level in the Agra sub-district division using the groundwater levels of neighboring sub-districts. And the coefficient that we want to estimate is rho hat. And as usual, we have the other covariates and the error term. And when do we use this model? Well, we use this model when we expect that some quantity is a function, is directly influenced by the same quantity in the neighborhood. So we believe the groundwater level at some position, at some location in space is directly influenced by the groundwater levels around it, then we should use this model. And the reason to believe that is because of hydraulic gradient. If groundwater levels are lower all around me, then water will tend to flow away from me into those areas, or the other way around. If the groundwater levels are higher or the hydraulic head is higher around me, the water will tend to flow in. So because of this subsurface flow, groundwater levels are spatially autocorrelated. So we try to capture this effect using this spatially lagged variable. This is also called the spatial lag model, simply spatial lag. And you might find other terms, but SAR or spatial lag model is most common. Well, you can also have the spatial error model, in which case your primary model remains the same, but your error terms are spatially autocorrelated. Now, what's the difference between this model and the previous one? Well, this model is saying that there is spatial autocorrelation in the errors of each observation, meaning that the spatial autocorrelation is coming from unmeasured factors. It's not coming directly from variables that we include, but from unmeasured factors, which is different, which is a little different from when the spatial autocorrelation is coming from direct relationships between the dependent variable at various locations. We don't know the source of this, so we do believe that the groundwater levels are spatially autocorrelated, but we don't know why. And we don't include any variables in our regression model to capture that. So it's gonna kind of sit in the error term, and this is when if that's our belief about the process, then this model is most appropriate. And then the third one is also a spatial lag model, but the spatial lag is not in the dependent variable; it's in the covariates in X. So it's sometimes called spatial SLX, spatial lag in X, where we include along with the covariates. So remember, X, beta, these are the covariates at the same location. So if Y is groundwater level at location I, then X is rainfall, temperature, and cropping at the same location. But theta, which is WX, the second term, WX, this is rainfall, temperature, and cropping in the neighbors, in the neighborhoods of I. Right? So we include both. So we believe that groundwater levels at location I are explained by rainfall, temperature, and cropping at location I, and by rainfall, temperature, and cropping in the neighboring locations, which is a kind of reasonable assumption, because we do expect that in the neighborhood, if it rains a lot, or if it's very hot, or there's a lot of cropping going on, we do expect these geographical climatic phenomena or the anthropogenic processes to be spatially related, to make an effect felt at this location. So we will run this model. Now, usually in realistic situations, you have one or more, or two or all three of these effects happening simultaneously. And for those, you need more complex models. But to start with, it would be good to get a grasp on these three simple models, how to run them in R, and try to interpret the results before you start combining things. So if that's clear, I'm going to move on to the coding session. If it's not clear, please do pause now, go back and listen to this video again, maybe another video in the course where Dr. Gaurav Arora talks about these models. Please review your materials at this point, and when you come back, I'll be right here. So I'm going to go ahead to the coding session with the understanding that all of us are kind of clear on these matters. All right, so before I go to today's code, I'm just going to briefly review our code from last time. So remember, as the step one, we kind of prepared our spatial data. We first read in some data from a CSV file that has data on post-monsoon groundwater levels, rainfall, temperature, and cropping. And then we converted it to spatial data, and then we loaded our, let me get rid of this plot. Then we loaded our state boundaries or sub-district boundaries for Uttar Pradesh. We aggregated our data to these boundaries, so we have a value for every sub-district as opposed to a value for every well. So we aggregated the well level observations to a higher sort of unit. And then we did some other work with the data, and we sort of plotted our data. So this is what the post-monsoon plot looks like. Now notice that one of the sub-districts, there's no data here. So this data is missing, so this will cause problems for us later on. So what I'm going to do is I'm going to take this district out of, I'm going to take it out of the data set. And that's what I'm doing here. I'm going to remove the unit with missing data. So if you remember, we'll use this condition. Dot is NA is a way to check if an observation is missing. And when I say not is dot NA, that means if I want only those where the observations are not missing. So I only want available observations for post-monsoon. So I only want to keep the rows where post-monsoon observations are available. If it's missing, I don't want that. So I think that gets rid of the one district. So I create a new data set, UP level 3 dot spatial dot 1. So dot 1 is the one where there's nothing missing. So that's the data set that we will use going forward. And then we built our weights matrix, and we visualized the weights matrix as follows. So please see that now for this district where data was missing, this is not part of the weights matrix. It's not, because we've taken it out of the regression completely. So if this is clear, now that we have our spatial data, we have our weights matrix. Our weights matrix is contained in this variable called w.listw. We can start to run our regression models. This really, all of this should be completely clear. If any of this is missing, then what's coming is not going to make a lot of sense. So please do review as many times as you need before going forward. All right, so this is our regression equation. We want to regress the post-monsoon level, that's our dependent variable, on the rainfall of this year's monsoon rainfall, this year's summer temperature, and last year's cropping. Those are the three variables. Those are our three covariates. That's our basic regression equation that we would use in a ordinary least squares if there was no spatial component. So that's what we'll do first. We'll first run ordinary least squares to see what kind of results we get. And this is done with, as you know, with the command lm. And then let's look at the results. So what we see is that rainfall is highly significant, and the sign is negative, which is good news. So you might, if I may just tax you with a small exercise, what does it mean that the sign is negative? You might pause the video and think about it for a few seconds before you come back. We're seeing a significant coefficient for rainfall, this year's rainfall, and the sign is negative. And what that means is that if rainfall, that the rainfall is sort of inversely related to groundwater levels. So I mean, in areas where there's rainfall is high, meaning the magnitude of rainfall in meters is high, at those locations, the value of groundwater level is less, is smaller. So groundwater level being smaller means that the water is closer, the depth is smaller, so water is closer to the ground, which is what we expect in very humid, wet areas. We expect water levels to be shallower, lower, right? And in areas where rainfall is small, like areas that border on Rajasthan or hotter areas, drier areas, we expect groundwater levels to be much deeper, so the value of depth will be higher. So that's what the negative sign is telling us. The other two variables don't seem to be very significant, although the sign of percentage cropping seems to be correct, that if there's more cropping, then we expect groundwater level to be deeper. And the sign of temperature is negative, which means hotter areas have shallow groundwater level. That's counterintuitive. But first of all, we must realize that this model may not be correctly specified. We may have omitted variable bias. We may have other problems in addition to spatial autocorrelation. So while I'm interpreting these results for you, they may not necessarily be interpretations that we want to use for analysis or for gaining any kind of understanding. This is just a demonstrative discussion of how we might interpret regression results. All right, so now what we want to do is, well, before we start running spatial regression models, we have to understand, are they even required? Do we even need spatial regression models? Maybe this ordinary least squares is good enough. So what we do for that is, what we can do, we can do a lot of things, but the one thing we can do is, one of many things that we can do is we can try to look at the residuals. So from this ordinary least squares regression, we can pull out the residuals. So we will have a residual for every subdistrict, right? Because we have 213 observations, which you can see from here. Well, we can, here it says 209 degrees of freedom because we have 4 variables. So the number of observations we can see from here in our data is 213, right? So for each one of these, we will have a residual. And we want to see if these residuals are spatially autocorrelated. So if there is some residual spatial autocorrelation, then that means that the ordinary least squares is not good enough. We need some spatial model. That means there is some residual spatial autocorrelation that is not being captured by the model. So let's look at, so we can get the residuals using this command here and store it in a variable called residuals, and then we can plot those residuals and see if, so what does that look like? I mean, now that we've gotten used to looking at spatial data, does that look like random, like a spatially random distribution, or is there some spatial autocorrelation? Well, it does seem that there is some clustering, that there are areas of where the residuals are high, like here and here, maybe here, and then there are other areas where residuals are 0, close to 0, and others where they are negative. So areas of positive residuals, negative residuals, and 0 residuals seem to be clustered together, which signals spatial autocorrelation. So what we can do is we can compute the Moran's I for the residuals to really get a sense, a quantitative measure. And we see that the Moran's I is 0.4, which is not necessarily very low. There does seem to be positive spatial autocorrelation. P-value is pretty low. So it does seem that we have some residual spatial autocorrelation. So we might benefit from running spatial regression models. So let's run our first spatial regression model. So let's go with SAR, the autoregressive model first. So the command to do that is lag SAR-LM. So lag means spatial lag, SAR means spatial autoregressive, LM means linear model. And this is available in the spatial reg package. So you can look at the help file for this by typing this. And this is available in the spatial reg package. So you can look at the specification here. So it gives you a little explanation and then shows you how to use it. Here what I'm doing is I'm passing in my regression equation, which is the same as before, the data, of course, and one additional parameter, which is the weights matrix. Because remember, now on the right-hand side, we have a spatially lagged variable. So obviously we need to pass in the weights matrix. Otherwise, R cannot compute that spatially lagged variable. So let's run this model and look at the results. So now we see sort of something interesting, that none of the so as before, temperature and percentage cropping is no longer significant, whereas rainfall is So remember, this is rainfall at this location, at the current location, is still significant. The p-value is 0.01, which is less than 0.05. So, but the coefficient is actually much smaller in magnitude. So it went down from -20, which was in the value in OLS, to -5. So that seems to indicate like a bias. And then the rho, which is the coefficient of the spatially lagged term, is 0.74, and it is significant. The p-value is close to 0, and that seems to be fairly high spatial autocorrelation. That's close to a value of 0.8. So we see that the spatially lagged term has a fairly high explanatory power, that it takes away the explanatory power of rainfall. So we see that not only are groundwater levels in this region influenced by rainfall in this region, but also strongly influenced by rainfall by groundwater levels in the neighboring regions. And then it gives us some more information here. So for example, the one thing that it gives us is the AIC criteria. I don't know how to say the name, so I won't say it. So the AIC criteria is 1153.8 for this model and 1248 for the linear model. So the AIC criteria is slightly higher for ordinary OLS and slightly lower for this. So, well, we want to know, did we do any better? Did we catch more of the? Is there residual spatial autocorrelation now that we accounted for some spatial relationships? So we can repeat the same exercise. We can get the residuals for this model and then plot them, and then see whether there is still. So we still see some spatial clustering. We see high residuals in these areas, but there's a little less clustering in areas of low or negative residuals. It's a different picture from the previous one, but we still don't know. So we can run a Moran's eye test and see. So now we see that the Moran's eye test is actually not even that significant, and the statistic has a very low value. It's close to 0.04. So it seems that residual spatial autocorrelation has reduced significantly from the ordinary. So that means that potentially means that we did a little better at capturing spatial relationships. So we can now repeat the same process for our two other models. So this is the SLE model. The command is error, SARLM, same as the previous name, except the word lag has been replaced by the word error, and it has the same parameters. We also pass in a tolerance because it's an iterative algorithm. So let's run that and store it in an object called fit.sle. This is our spatial error model, and then run a summary of that. So what do we get? So rainfall is still just about significant. The value is different from both the ordinary least squares and it's kind of between the spatially lagged model and the ordinary least squares. So ordinary least squares -20, spatial lag was -5, now it's -10. Again, close to 0.8, and it's significant. So that means that that the error terms also had some spatial autocorrelation. So let's see if the Moran's eye for that kind of is. So let's plot the residuals, and let's see the Moran's eye. So the Moran's eye is again not significant, and it's close to 0. So that model also helps us. It somehow helps us to capture spatial autocorrelation more than the ordinary least squares model. Now we can run SLX, and if you do a summary of this, So what you'll see is that you get the usual coefficients, which are the rainfall temperature and percentage cropped area for this location, and then lagged versions of all of them. And now we see some interesting results. So we see temperature becomes significant in the sense that, and it has a positive sign. So that positive sign is something that we can interpret in the sense that hotter areas will tend to have higher groundwater depth. So that actually makes sense. And somehow when we didn't have this result when we didn't include the spatially lagged temperature variable. But if we include spatially lagged temperature variable, then we have a significant coefficient. But interestingly, the lag temperature variable has a negative sign. So that means, so you'll have to think about what that means. What that means is that while if it's hotter here, the groundwater level here will be deeper. But if I'm surrounded by cooler areas or hotter areas, then the temperature here has a direct relationship, but temperature in the neighborhood has an inverse relationship. So that's counterintuitive, and so I would re-look at what model I would use for this. Similarly, we see that lagged rainfall has a very high negative sign, and it's significant. So that means groundwater level here is inversely strongly related to rainfall in the neighborhood. And then we can do the same thing. We can plot the residuals for this and run a Moran's eye. So for this, we still see residual spatial autocorrelation. So this model doesn't necessarily get rid of the spatial autocorrelation like the spatially lagged and the spatial error models did. One could argue that what that means is that we should probably go with the spatially lagged or spatial error models, and this is not necessarily the correct model. But in reality, I think the best approach would be some kind of mixed model, because rainfall in the neighborhood is important, temperature in the neighborhood is important, as well as groundwater levels in the neighborhood. But before you start mixing and matching models, I would encourage you to get a firm handle on how to prepare your data, your weights matrix, and how to run these models and start interpreting the results before you go forward. So that's all I had for today's coding session. Just to summarize, if you can help me summarize, what did we do? We ran OLS and 3 simple spatial regression models. We compared the results we ran. And how did we compare the results? By doing visual plots of the residuals and running Moran's eye tests for residual spatial autocorrelation. I'm going to leave you here. Thank you so much for your attention.